today's video, we're going to be talking about Gaussian beams, which is the type of beam that one finds in a laser. So this here is a helium neon laser produced by Thor Labs, and I wouldn't recommend doing this at home, but here with the camera, we are zooming in on the laser and looking right into it. A lot of those things that you see are just artifacts. So the reason it's called a Gaussian beam is because of the shape of its cross-section. This is the power versus position plot that you would get if you measured its power, say, with a camera, as we're going to do in just a couple minutes. The power versus position is roughly the shape of a Gaussian distribution or a normal distribution, and as you can see from the shape of this, it has a peak in the middle, but then it slowly decreases and then bleeds off gradually to nothing. So when we talk about the diameter of a Gaussian beam, we have to somewhat arbitrarily define a point to call the edge, and in this case we're going to do it using the 1 over e squared diameter. We are looking for the point where the power falls to 1 over e squared of the peak power. Now that's about 13% of the peak power. If this is a real normal distribution or a real Gaussian distribution, then this is going to be a total width of 4 standard deviations. So one standard deviation takes you from the middle out to about over here. To investigate this in the laboratory, we are going to start with the laser with a 40 millimeter focal length lens in front of it. So that produces a beam, and to take measurements we're going to use a camera. That little rectangle that you see in the center is the sensor. We're going to put the camera on an optical rail so that it sees the beam that's coming out of the lens, and we can move the camera up and down easily on this rail to look at different sections along the z-axis of the beam. And the rail has markings on it that lets us move the camera to a pretty precise location. So now I want to introduce you to a little tool, an application that I whipped up in MATLAB called Gauss Mouse. And this is just a way to automate the collection of data about beam profiles. So here we have a live image of what the camera is seeing. Just put my hand in front of it. This is the camera sensor is about 3.5 millimeters tall by about 4.5 millimeters wide. So this spot is roughly 2 millimeters in diameter. Those red lines indicate what we're calling the edges of this beam. And right here is, it says 2.1 millimeters. So as you can see, the beam is a little bit messy. We have some ripples in there that probably are coming from dust. My lab is pretty dusty, and I think there are also some other sources of noise, and it doesn't really look quite Gaussian, but we're going to be pretty sloppy and just call that good enough. I'm happy with that for this application. I'm going to set the exposure time so that we don't have any saturation. Now, as I move the camera around on the rail, the size of the beam changes, and that's the data that I want to collect. I want to get the size of the beam versus the Z position of the camera. So I'm going to start this by moving the camera right up close to the 40 millimeter lens. And here the spot is really very small. So I'm going to zoom in so that we can get a better image of the spot. I need to tell Gauss Mouse what the Z position of the camera is. and I'm going to give it an increment. And so when I tell it to collect a data point, it's just simply going to log the Z position and the diameter of the beam. Now I need to manually scoot the camera a couple millimeters and then collect another data point. And I'm just going to continue doing this, manually scooting the camera by 2 millimeters and collecting more data points. Okay, so this has given us a pretty high resolution, or high enough resolution profile of the beam diameter in the waist region. So these are meters, so this is what, maybe 25 millimeters roughly, a 25 millimeter long stretch of the beam, and at its narrowest point it is about, well, let's click Analyze Waist. Okay, so at it fit this green line to it. That's what it's thinking is the best fit to these data points. And yeah, about 68 microns or something is the narrowest point. And now I'm going to start looking at a very different region. So I'm going to zoom out again, and I'm going to scoot the camera into the cone region, which is far enough away from the waist that you don't get any more of the waist shape effects. Rather, we're just going to be looking at the divergence of the beam, and we're going to go far enough away that it's effectively in the cone region of the beam. And just like in the waist region, I'm going to zoom through a few more points here. I won't make you watch. So I'm going to fit a straight line to that, and that tells us the divergence. So what we have learned from this is that this particular beam has a divergence of about 13.2 milliradians and a waist diameter of about 68 microns. So now that we've got a little bit of data, let's compare our data against the theoretical or ideal shape of a Gaussian beam. So over here we have a diagram that represents what the theoretical shape looks like. Over on the right we've got a cone. Okay, and you can imagine this cone going off to infinity and just getting wider and wider. That angle, the angle that the cone takes up, is it asymptotically approaches a certain value, which is the divergence, which we can call theta. So the shape of the beam is essentially a cone, or really two cones, that meet at a point. But if you zoom in, it's not actually an infinitesimal point. Rather, the beam reaches a finite small size at the very center. And that point at the center is called the waist, and it has some finite diameter d. And that is the second parameter that characterizes a Gaussian beam. The third parameter is called the Rayleigh length. So this central region of the beam where the two cones touch has some length to it. And inside of that length, you can think of the beam as being focused. Outside of the length of that beam, it is expanding. And the width of that section in the middle is defined as the distance within which the diameter of the beam is equal to less than double the waist diameter. So at about this point, the diameter of this beam is double what it is at the waist, and then you have a similar point on the left. And so if your sensor or whatever is somewhere within 2 times the Rayleigh range, you can consider it to be in focus. Now, for a single wavelength beam, all three of these parameters are related by these two formulas. So that if I tell you the diameter, you can calculate the divergence in the Rayleigh length. Or if I tell you the Rayleigh length, you can calculate the diameter and the divergence. So this is true as long as the wavelength stays constant, and we're going to see as we play with these things and shine the laser through different lenses that we will be producing different beam sections that have different diameters and different divergences, but the wavelength always stays the same. So let's take a look now at the output of the laser that I've got. As I mentioned before, this is not a symmetric Gaussian beam. Rather, the waist is basically the output of the laser. So it has a waist right at the face of the cavity, and it's pretty wide. It is just about 0.5 millimeter, which matches the data sheet, and the divergence, though I'm not really very far away from the waist. I should have measured the divergence further away, but because I don't have a very long table, this is going to have to do it. The divergence here is about 1.75 milliradians. Again, pretty close to the value that is supplied by Thor Labs on their data sheet. So a moment ago, we shined the laser beam through a 40 millimeter lens, and now I want to look at what happens when we move to different types of lenses. So here we have the data from 3 different lenses. We have basically a small, medium, and larger focal length. The smallest one is actually a microscope objective. And I've switched to using a slightly different color convention, by the way. When we looked at this, when we looked at the output of the laser beam, I used green for the waist and red for the cone section of the beam, which is the way that Gauss Mouse does it in that little application. But in this case, when I'm comparing several beams at once, I've got both the cone and the waist for the 17 millimeter beam covered in red. Green is for both sections of the 40 millimeter beam, and so on. So throughout this presentation, I'm going to be kind of mixing back and forth between these two color conventions, and you just have to glean what is happening from the context. So what you see here, though, is that, not so surprisingly, the longer the focal length of the lens, well, we see two things. First of all, we see that the waist of the beam is further from the lens itself. In all these cases, the plane of the lens is over on the left side of the chart here. But we also see that the beams with a greater divergence have a smaller waist, and that as the focal length of the lens gets longer, we wind up with a beam that has both a larger waist and a shallower divergence. So let's take a look at the actual numbers here. Each of these columns is a different one of the beams that we saw in the previous slide. So the 17 millimeter focal length, the 40, and the 100 millimeter focal length. Now, their waist diameters, as we saw, vary quite a bit by about a factor of 6 from the smallest to the largest, and the divergences also vary by a factor of roughly 6. But when you multiply the diameter times the divergence, you get what is called the space bandwidth product. And here you can see that for all 3 of these beams, which are quite different in their wastes and diameters, the space bandwidth product is roughly constant. Now, the concept of space bandwidth product applies to all different kinds of light, not just laser light. It applies to a flashlight, it applies to a fire and a fireplace, but it is in the case of the Gaussian laser beam that you find the smallest possible space bandwidth product. So the ideal space bandwidth product, or really the minimum, is lambda, the wavelength, times 4 divided by pi, which in our case is 806 nanometers. And you see that we are a little bit above that, but not a whole lot. Now, we characterize actual laser beams with a number that is called the m squared value. The m squared value is the actual space bandwidth product divided by the ideal space bandwidth product, where this here is the ideal space bandwidth product. So in these experiments, we got values of m squared that are a little bit over 1, and that's pretty normal. So m squared can go arbitrarily high, but it cannot go arbitrarily low. The uncertainty principle, which is a core principle of quantum mechanics, limits the space bandwidth product to go no lower than the value we see here, lambda times 4 over pi. And for an ideal Gaussian beam that is entirely single mode and with no associated errors, that value is 1. And as the actual space bandwidth product increases, in the case of a real beam, the m squared value goes up. And it's designated as m squared rather than just m, because typically you think of both the diameter and the divergence as increasing by the value m. And so for the space bandwidth product, you would have m squared times the ideal space bandwidth product. So another way to think about the lens is that it can expand or condense the size of the beam. Now, you often think of a beam expander as something you can build by putting a pinhole one focal length in front of a lens. If you do that, then all of the rays that leave the pinhole come to the surface of the lens and are straightened out and go out straight. That is an approximation that's used in geometric optics, which is sort of a simplified theory of how light propagates. This is the same device, but it's viewed through the theory of Gaussian beam propagation. One of the properties of a lens is that it turns one waist into another waist. So if you place one beam waist one focal length away from a lens, it will convert the beam into another beam with a different waist in the other focal plane of the lens. And that is one way to think of a pinhole used as a beam expander. So you have a very small pinhole, which is a very small waist, and the input beam expands, and then the output beam, while it appears to be going out straight, it actually has a small curvature, which in practical situations may be barely noticeable, and it, at least in theory, has a beam waist one focal length away from the lens. And this is true regardless of the size of the waist that you use at the input. So as long as your waist is one focal length away, the second waist will always be one focal length away. It's also possible to put them other places and then these distances get funky, but these two planes are kind of the sort of the simplest way that the lens can be used. Now I also want to note you can use essentially this same device in reverse to create, for example, a focused laser beam. So often people want to focus a beam down to a small spot, for example, in something like laser machining, or if you need to illuminate something very intensely. In that case, you would use, you can essentially use this in reverse, where a large input beam is fed into the lens, and that it shrinks down then to a smaller output. So why does it work in one direction one way and the other direction the other way? That has to do with the sizes of these wastes. And let's discuss that by looking at some examples here. Now, the equation that determines the magnification or the size of the input or output beams is this one right here. The magnification or demagnification that happens from the lens is governed by how the Rayleigh length of the input beam compares with the focal length of the lens. And briefly, if the input beam has a Rayleigh length smaller than the focal length of the lens, then the lens will expand the beam. If the Rayleigh length of the input beam is larger than the focal length of the lens, it will condense or focus the beam. So let's take a look at a few examples just so that we get the idea here. The helium neon laser that we are using has a beam diameter at the waist of 480 microns, and using the formula that we showed earlier, that equates to it having a Rayleigh length of 286 millimeters. Now that 286 millimeters is a little bit larger than the focal length of the lens, which is 100 millimeters, and so it actually shrinks it. So using this formula, we get 168 microns as the diameter of the output beam. Now, what happens if we were to double the input beam? So going from 480 to 960. Well, first of all, the Rayleigh range itself quadruples, and the diameter of the output beam is cut in half. So double the size of the input, cut in half the size of the output. The next thing we're going to consider is what happens if you have a 150 micron input beam. Now, we are actually going to do this experimentally. This is something that you can do using a pinhole. So we're going to create a waist using the laser and a lens, and we're going to put a pinhole in the focal plane of that lens, which essentially creates a new waist. And we'll talk more about this later. But for now, just think of it as a beam with 150 micron waist diameter, and that has a Rayleigh range which is smaller than the focal length of the lens. It's only about 28 millimeters. And so following this formula here, we would expect that it would be larger than the input beam. It's about just over 500 microns. And this is interesting because we can see that the 480 millimeter input gives us about 150 micron output, and the 150 micron input gives us roughly a 480 micron output. It's a little larger, but these two beams are sort of inverses of each other. The lens converts either one into the other. And collect a little bit of data on that, and you can see that indeed the data matches roughly the theoretical predictions. So this green line is the measured output of the 150 micron input beam, and it's at about 500 microns. And this red line is the output beam of the 500 micron or 480 micron beam, and its waist is a little bit larger than 150. So things aren't precisely matching theoretical values. And the last case we're going to consider is the value, which is approximately 284 microns. In this case, the Rayleigh range is 100 millimeters, which is the same size as the focal length. And so in this case, the size of the beam is sort of matched to the size of the lens, And so the output beam is the same size as the input beam. So let's talk about a slightly more complicated device, which is the compound beam expander, which can also be used, of course, as a condenser. This is what you'll get if you buy a beam expander from an optics house. So there are two lenses. One of them has a short focal length, the other one has a long focal length. And you place them such a distance apart that the distance is the sum of the two focal lengths. So if this were a 10 millimeter focal length and this were a 100 millimeter focal length, you would place them 110 millimeters apart. And the way it works is that the input beam has a waist in the left focal plane of the first lens. It creates a smaller waist in the right focal plane of the left lens. And then this shrunken, demagnified waist is then used as the input beam for a second large diameter focal length lens. The shorter that the Rayleigh range of the input beam is, the larger the output beam will be. And the point of a beam expander is to get a really large output beam. So what you want then is a large focal length lens with a really small input beam. And the way to get a really small input beam is to shrink or condense the beam using an earlier lens. Let's try this in the lab. Our first lens is a microscope objective with a focal length of 17 millimeters. It focuses to a point quickly and then expands quite rapidly. And our second lens will be a 100 millimeter focal length lens. The distance between the two lenses is what governs the output of the overall system. If you look at a wall a few meters away, you see that moving the second lens changes the shape of the spot quite a bit. Let's start by looking at the beam profile when the lens is at 275 millimeters. Here we see that it's diverging, and it's diverging fairly rapidly. Now when we move the lens to 255 millimeters, which is further to the right, we see two things. We see that because the lens is further to the right, the nearest point where I've been able to capture any data is also scooted over to the right. But we also see that the divergence is less. Moving that now over another 20 millimeters to 235, we see that it's pretty much flat. And this is going to be the point where it essentially has its best collimation. As we continue to move it to the right, at 215, we see that the beam has now started to converge. And when we move it even further to 195 millimeters, that continues. And finally, it converges enough that I'm actually able to capture the point of the convergence on my relatively short rail. We're going to look now at another way of transforming beams, and that is using pinholes. So a pinhole is just a small opening, and what you do is form a beam waist using a lens, and then place the pinhole in the plane of the beam waist so that it clips the beam and forms a smaller spot. Now, what you get when you do this is something not exactly similar to the Gaussian beams that we've looked at up to now, but close. So I did this with several different pinholes. We have the 20 micron pinhole, the 50, and the 150 millimeter pinhole, and they look quite similar to Gaussian beams in that the smaller the pinhole, the steeper the divergence. And so it's nearly the same thing as if we had made a pinhole of, say, a 20 micron diameter by focusing it with a lens. However, we do see a little bit of a difference when we look at the space bandwidth product and the m squared value. which tells us how close the beam is to ideal. Earlier, when we were transforming beams with lenses, we saw that the m² values ranged from 1.05 up to 1.19. And remember, the ideal m² value for a perfect Gaussian beam is 1. But back to the values that we found when using a pinhole, they're significantly higher. Still pretty low, but higher than we saw before. And this can be attributed to the fact that when you clip a beam, it no longer has the same Gaussian shape that a true Gaussian beam has. So it's a clipped version of that beam, and that means that when you decompose it into a set of basis functions, which are the Gauss-Hermite functions that we haven't discussed, it turns out that the beam is made up of other modes other than just the Gaussian normal distribution type mode. Instead, it also has some components that are higher and more complicated modes, and that results in our seeing these larger m² values. If instead of a pinhole we were somehow able to use a partially absorbing pinhole, something that could, instead of just totally blocking the light or totally passing the light, if it could absorb part of the light, if you had a pinhole that had these partially transparent regions so that it gave you a Gaussian shape, then these values would likely be lower. They would probably be close to what we saw when we were focusing Gaussian beams with lenses. Similarly, I want to talk about multimode lasers. So this is a laser pointer of the kind you might buy in a store. This is made with a laser diode, and laser diodes are solid-state lasers that tend to have a more complicated mode structure than the helium-neon beams we've been looking at up to now. So here we see the Gauss mouse data from the diode laser in red and from the helium-neon laser in green. And the helium-neon laser is a little bit wider at the waist, but much shallower in the divergence. These are both using the same type of lens. And here we can quantitate this. The helium-neon laser had an m² value of 1.05. The diode laser, over 4 times as great, 4.7. So you see a very big difference there between those two different types of beams. As always, there's a lot more to talk about, but not enough time to talk about it. So we're going to have to wrap up for today, but thank you for tuning in. I hope you enjoyed the video, and please come back again for more videos in the series.